You know, when we think about the giants of technology, a few names always pop into our heads, right? So, first up, you've got the architects. Of course, we all know NVIDIA. They're the ones designing the GPUs that power this whole AI revolution. They literally dream up the blueprints for our digital world. But a blueprint is just an idea. You need a forge to make it real. And that's TSMC, the powerhouse foundry over in Taiwan. This is where those amazing designs from Silicon Valley get turned into actual physical chips. They're the builders. Okay, but to build something that complex, you need an artist with an unbelievable brush. And that's the Dutch marvel, ASML. They make the only machines in the world, these extreme ultraviolet lithography machines that can paint those impossibly tiny circuits onto silicon. Architect, forge, painter. Sounds like we've got the whole picture, doesn't it? But hang on. It brings up a really basic question. What are they painting on? What's the canvas? What's the one thing that all of them, without exception, have to have? Well, the answer is hidden deep down in what you might call a subterranean economy. See, beneath all these famous companies, there's a bedrock of suppliers working completely out of the spotlight, and without them, the whole digital world just stops. And at the absolute bottom of that bedrock, you find this, the silicon wafer. It is the most fundamental piece of the entire digital economy. Think of it like this. Before you can even think about a single transistor, before any code can run, you have to have a perfect, absolutely flawless canvas to print it all on. So, who makes the canvas? It's time to meet the most critical company in the semiconductor supply chain that you've probably never heard of, Japan's Shin-Etsu Chemical. And when I say critical, I mean dominant. The numbers here are just staggering. Shin-Etsu, along with its main rival, another Japanese company named Sumco, controls more than half of the entire global market for these wafers. Yeah, the foundation for the whole world's digital infrastructure is, for the most part, made in Japan. So how on earth did they get so dominant? Well, it's not just about cornering a market. It's about mastering a kind of modern-day alchemy. It's a crazy, relentless quest for a level of purity that is almost impossible for our brains to even comprehend. This is the number. This is the industry standard. It's called 11 nines purity. That means 99.9999999% pure silicon. And that's not just, a nice goal to have, it's a hard requirement. Why? Because just one single atom out of place can destroy a multi-million-dollar chip. Let's try to wrap our heads around that. Finding one impurity atom in a finished wafer is like trying to find one single specific person out of all 8 billion people on planet Earth. Just think about that for a second. That's the level of perfection Shin-Etsu has to deliver day in and day out. It's insane. And they do it using something called the Czochralski process. It's this beautiful, delicate dance of physics. First, they melt down super pure silicon. Then they take a tiny, perfect seed crystal and dip it into the molten goo. And then, ever so slowly, they pull that seed up while spinning it. The liquid silicon cools and solidifies around the seed, copying its perfect atomic structure. What you get at the end is this massive, perfectly structured single crystal ingot. It's beautiful. Now here's the real magic. Shin-Etsu's edge comes from decades of obsessively perfecting every single step. They have their own secret tweaks to that process. They use specialized heating techniques, it's called annealing, kind of like baking the silicon to iron out any tiny microscopic voids. And they have an absolute mastery of creating these layered, flawless wafers that the world's most advanced chips absolutely depend on. And all of this expertise, this mastery, it creates something that's strategically critical and maybe even a little dangerous, a hard choke point in the global supply chain. It makes them, for all intents and purposes, irreplaceable. I mean, you can't just wake up one day and say, I'm going to start a silicon wafer company. It's not like a software startup where you need some smart people and a few $million. We're talking billions with a B in capital just to get started. And even more important than the money is the decades of deep institutional knowledge that you just can't buy. It has to be earned. And here's the really stark reality of it all. If Shin-Etsu's factories just stopped tomorrow, the entire global tech industry would grind to a halt. The production of everything from your iPhone to an F-35 fighter jet, it would just seize up. All their competitors are already running at max capacity, and honestly, a lot of them can't even match the quality. There is no backup plan. So, Why are we talking about this? Why does one company in Japan matter so much to every single one of us? Because it pulls back the curtain on this hidden global tether, one that connects geopolitics, the world economy, and yeah, the phone that's probably in your hand right now. There's a term for this: weaponized interdependence. When you get this level of extreme specialization, you create these incredibly powerful choke points. All it takes is one factory fire, one bad diplomatic argument, one natural disaster, and suddenly one company or one country has immense power over the rest of the world. So what's the big takeaway here? It's that our super advanced, high-tech world is built on this foundation of insane specialization. And that creates these hidden, powerful choke points with huge geopolitical consequences. It shows you that our entire digital economy has this hidden fragility to it. And at the end of the day, it means the world's most famous chip makers, Intel, TSMC, Samsung, they are all tied, completely tethered to what comes out of Shinizu's furnaces. This is honestly the best way to think about it. Every computer chip, right? It starts out as just a blank slice of silicon. It's the canvas. But to get those unbelievably tiny circuits on there, the things that actually make it work, you have to paint on it. And that paint is a special light-sensitive chemical called a photoresist. And the whole process of using that paint, it's called photolithography. You can think of it as a kind of microscopic photography. It literally prints the blueprints for all the transistors and circuits directly onto the silicon. Without this chemical, you just can't make a chip. It's the absolute linchpin of the entire thing. So how does this actually work? Well, it's this incredibly precise three-step dance. First, you coat the silicon wafer with a perfectly smooth, thin layer of this photoresist. Then, you blast a pattern of light onto it, which actually changes the chemical structure. And finally, you just wash it away. What's left behind is a perfect stencil ready to be etched into the chip itself. It's pretty amazing. Now, this is where it gets really, really interesting. Who has actually mastered making this incredibly complex chemical paint? Because this is not something you just whip up in a lab. We're talking about decades of specialized knowledge. At their peak, a small group of Japanese companies controlled a staggering 90% of the entire global market for this stuff. Now, let's be clear, that's not just a market lead. That is a level of control that's almost unheard of for something so critical. It's basically a cartel for the foundational chemical of all modern tech. The whole market is pretty much run by these four giants: JSR Corporation, Tokyo Oka Kogyo, or TOK for short, Shin-Etsu Chemical, and Fujifilm. These are the gatekeepers. They are the masters of the medium that everyone, and I mean everyone from Intel to Samsung to TSMC, completely depends on. So to really understand this dominance, let's zoom in on two of these players, JSR and TOK. They have totally different strategies, but they are both absolutely essential to the global supply chain. Okay, so you've got JSR. They are betting everything on the future. They're the pioneers in the chemicals needed for the most advanced chip-making process, EUV lithography. We're talking about the stuff you need for 2-nanometer chips that will power the next generation of AI. But then you have TOK. They're the masters of the present. They are the indispensable backbone for the billions of older, so-called legacy chips that run, well, everything else, from your car to your dishwasher. And this chart just shows you TOK's power perfectly. For the older but massive volume manufacturing processes, they have huge market share. So a problem at TOK wouldn't just delay some fancy future AI chip. It would literally halt the production lines for things like the Toyota Camry and the Sony PlayStation. And this gets us to a really crucial point. This invisible chemical, it isn't just for supercomputers and high-end tech. It is quietly hiding in almost every single piece of technology you touch every day. I mean, just think about it. The little microcontrollers that run your car's engine, the main processor in a gaming console, the NVIDIA GPUs that are training all these AI models, even the simple power chips in your washing machine and the sensors in medical gear. Not a single one of them can be made without photoresists. And here's another wild example. Remember Fujifilm and their camera film? Well, they pivoted all that chemical expertise into making colored photoresists for camera sensors. And today, their niche tech is so good, they essentially control the quality of almost every single smartphone camera out there. So, let's recap. We have an absolutely essential material controlled by a tiny handful of companies, all located in one country. You can probably see where this is going. This intense concentration has created a hidden and, frankly, incredibly fragile global vulnerability. The logical question, the one you're probably thinking, is, okay, if it's that important, why don't countries and big companies just buy tons of it and store it away, like they do with oil reserves? The answer is one simple and kind of devastating word. It's perishable, right? Unlike something stable like a bar of silicon, photoresists are these super complex chemical cocktails, and they have a shelf life of only 3 to 6 months. They have to be kept at very specific, very controlled temperatures. You can't just stick this stuff in a barrel and save it for a rainy day. It's more like a living, continuous flow of material that has to be constantly produced and shipped from Japan. So what this means is that the entire global semiconductor industry is operating on a just-in-time dependency. It's relying on this fragile, unbroken tether that stretches all the way from a few chemical plants in Japan to chip factories all over the world. And this creates a terrifying single point of failure. A lot of this production is clustered in the Chubu and Kanto regions of Japan, areas that are, prone to major earthquakes. One big quake there could shut down production instantly, and the entire global supply, it would dry up in just a matter of months. Let that just sink in for a second. A single natural disaster in one very specific part of the world could bring the production of nearly all modern technology to a screeching, grinding halt. Which brings us right back to where we started. In that scenario, the world's multi-billion-dollar semiconductor fabs, some of the most advanced factories humans have ever built, would just go silent. They'd have the canvas, but they would have absolutely no paint.
Well, it's not just one thing, it's a whole category of them, invisible ingredients. We're talking about hyper-specialized gases, and honestly, their story is a wild ride that reveals just how precarious our modern world really is.
Okay, so our first story kicks off right in the middle of a war zone, and it shows how fast geopolitics can throw the entire semiconductor industry into absolute chaos. So, let's meet our first invisible ingredient, neon. Now, its job in making a computer chip sounds simple, but it is absolutely critical. Inside the super powerful lasers that etch tiny circuits onto silicon, neon acts as a buffer gas. The best way to think of it is like a bodyguard, protecting the laser's super delicate and expensive parts from getting fried.
But here's where it gets crazy. The level of dependency the world had on one place is just staggering. Before 2022, a whopping 90% of all the semiconductor-grade neon used in the United States came from Ukraine. Now, this wasn't really by some grand design. It was actually a weird historical leftover from the Soviet era, when these massive steel plants were built with the side hustle of capturing rare gases like neon.
And this just laid the risk bare for everyone to see. I mean, after the 2014 annexation of Crimea, neon prices shot up 600%. That was a huge warning shot. But when the full-scale invasion started in 2022, the two main Ukrainian suppliers, companies called Ingas and Cryoin, had to shut down. And just like that, the global chip industry was thrown into a full-blown panic.
Just let that sink in for a second. The most sophisticated technology on the planet, the stuff that powers everything from AI to our national defense, was completely reliant on a waste gas from old Soviet steel mills sitting in the middle of a 21st century war zone. You can't make this stuff up. Now you might be thinking, okay, a war is a pretty extreme example, right? A total black swan event. But what if I told you this level of fragility is actually baked into the system, and that it can be triggered by something as simple as a single spark?
So, was the neon crisis just a 1 in a million fluke? I wish. Now, this kind of vulnerability is, unfortunately, a fundamental feature of the whole system.
Let me introduce you to our second character, nitrogen trifluoride, or NF3 for short. So if neon is the bodyguard protecting the laser, NF3 is the janitor. See, after each layer is put on a silicon wafer, the inside of the manufacturing tool gets all gunked up with residue. NF3 is the workhorse gas that scrubs the chamber spotless so the next wafer comes out perfect. Without it, these multi-million-dollar tools become useless in just a matter of hours.
And you guessed it, just like with neon, the supply is incredibly concentrated. There's this one Japanese company, Kanto Denka Kogyo, that's a true invisible titan, a name you've probably never heard, but a company that holds enormous power. It controls over 90% of the market in Japan for this super pure NF3, and it's a key supplier to global giants like Samsung and Sony.
So what happens when something goes wrong there? Well, a single fire at just one of Kanto Denka's plants in Japan suddenly threatened to choke off the supply of this essential cleaning gas to the world's biggest memory makers. Think about that. An industrial accident in one town could have made the price of your next phone or laptop go through the roof.
Okay, so these two stories, Neon and NF3, they're really pointing to the same underlying problem. So let's zoom out for a minute and look at the fundamental reasons why this whole system is just so darn fragile.
First up is the purity problem. And we're not just talking kind of clean gas here. We are talking about mind-blowing levels of purity. 99.9999% pure, or what's known in the industry as 6-nines purity. Why? Because the tiniest, most microscopic impurity can ruin millions of dollars worth of chips in an instant. Getting gas this clean is unbelievably difficult and expensive.
And that leads directly to the switching problem. Because that purity is so vital, you can't just call up a new supplier if your main one goes down. A chip factory, or a fab, has to spend 6 to 12 months rigorously testing and qualifying any new source of gas to make dead sure it won't contaminate their whole production line. The industry just can't turn on a dime.
So when you start connecting the dots, the picture becomes painfully clear. The whole system leans on obscure byproducts, it demands impossible levels of purity, it takes forever to adapt to change, and production is often stuck in one small part of the world or in the hands of a few of these invisible titans. This whole situation is forcing companies and governments to finally wake up and react. They're looking at everything from stockpiling these materials to desperately trying to find more suppliers.
And look, when we say a few companies, we are not exaggerating. The entire global market for these critical gases is basically dominated by a handful of players. We're talking about companies like Linde, Air Liquide, and Taiyoni Pansanso. It is an incredibly concentrated, high-stakes game.
So what's the big takeaway here? What does all of this really tell us about the world that we've all built?
The reality is our entire high-tech society is balanced on this invisible web. It's a vast network of materials, companies, and supply chains that we never ever see, but that we depend on for pretty much everything we do.
And as we've just seen with Neon and NF3, a lot of the connections in this web are just single fragile threads, and they could snap at any moment, not just from a war, but from a factory fire, a natural disaster, or just a sudden change in global politics.
So here's the big question. How in the world do you polish a surface with Angstrom-Level Precision? We're talking about a flatness measured in single atoms. I know, it sounds completely impossible, right? But that's the core challenge behind every single modern electronic device we use. Okay, so first, let's really get a handle on the problem. Just imagine for a second that you're trying to build a perfectly stable, massive skyscraper, but the foundation you have to work with is this rugged, totally uneven mountain range. Yeah, that's exactly the kind of issue chip makers are up against. See, a modern chip isn't just one single thing. It's more like a tiny, bustling city of transistors and wires, built straight up, layer by excruciatingly thin layer. This whole stacking process is what lets us pack more and more power into smaller and smaller spaces. And each new floor of this microscopic city gets built using a process called lithography. But here's the catch. With every single new layer you add, the surface starts to develop these microscopic hills and valleys. It gets bumpy. And if that surface isn't perfectly, and I mean atomatically flat, the next layer of circuits you try to print on top, it's just going to be out of focus. The whole thing fails. The entire chip becomes a tiny, very, very expensive coaster. All right, so how do they solve this massive problem? Well, they use a process that honestly sounds like a complete contradiction. It's called chemical mechanical planarization, or CMP for short. To put it simply, CMP is basically the industrial art of polishing a silicon wafer until it is absolutely flawlessly flat. This one step is the key. It's what allows chip makers to just keep stacking those layers higher and higher, making our chips more and more powerful every year. Now, the process itself sounds surprisingly straightforward when you break it down. You take a wafer, which holds hundreds of individual chips, and you press it face down against a big spinning pad, kind of like a record on a turntable. Then you flood the surface with this special liquid called a slurry. And that combination of chemical action from the liquid and the mechanical force from the pad grinds the surface down to a perfect finish. And that's where you really see the heart of CMP. People call it brutal elegance. It's brutal because you are literally physically grinding away material from this unbelievably delicate surface. But it's elegant because it somehow manages to stop with Angstrom-level precision. Just to put that in perspective, an angstrom is 1/10,000,000th of a meter. We are talking about the width of a single atom. It's this incredible dance between raw force and unbelievable finesse. And believe me, the stakes are just immense. This is a total high-wire act. If you polish just a little too aggressively, you create something called dishing, where you actually scoop out the delicate copper wiring. But if you're too gentle, you leave material behind, and that causes short circuits. Either way, the chip is dead. The margin for error is, well, it's pretty much zero. But it's not just about the big polishing machine. The real magic, the absolute secret to getting this incredible precision, it's all in the liquid. So this liquid, it's called a slurry. And it's not just any liquid, it's a highly, highly engineered chemical cocktail. Its job is really twofold. First, it has to chemically soften the surface of the wafer, and then it has to mechanically scrape it away using tiny, tiny particles. So if you could look inside just one single drop of this slurry, you'd find a few key ingredients. First up, you've got these abrasive nanoparticles, usually made of something like silica, and they're the ones doing all the physical scrubbing. Then you have chemical etchants that are designed to weaken the material you're trying to polish. And finally, there's this really complex mix of additives whose only job is to protect the layers underneath that you absolutely do not want to touch. Okay, now I want you to think about just one number, the number 1. Because in the world of CMP, that one single number can be the difference between a successful billion-dollar production run and a giant pile of useless scrap. Because all it takes is one single rogue nanoparticle in that slurry. Just one particle that's a tiny bit larger than the billions of others around it. If that one particle drags across the wafer, it creates a scratch. And that one tiny scratch, that's what they call a killer defect. It completely destroys the entire chip. Game over. So this crazy level of sensitivity means that creating a perfect, totally defect-free slurry is an incredibly valuable skill. And it turns out, only a handful of companies on the entire planet have actually managed to master it. And that makes them these hidden, unsung giants of the chip world. The undisputed king, the titan in this space, is a Japanese company called Resonic Holdings Corporation. They were formed from a merger of two chemical powerhouses, Showa Denko and Hitachi Chemical. Now, Resonic is probably a name you've never heard of, but I guarantee you, every single major chip maker on Earth depends on them. And Resonic's dominance here is just staggering. They make specialized slurries for pretty much every material used in a modern chip, everything from copper to tungsten to dielectrics. They're also huge in advanced packaging materials. And they're not sitting still. They are pouring massive amounts of R&D money into developing the next generation of slurries for those cutting-edge 2-nanometer chips, which are going to use totally new materials like cobalt and ruthenium. Now, while Resonic is definitely the leader, they're not completely alone. This is a very concentrated market, dominated by just a few masters of the craft. You've got Fujimi Corporation, also from Japan, and the US-based company Integris, which used to be Cabot Microelectronics. These are really the only other key players who have perfected this technology over decades and decades. So you gotta ask, why is this so ridiculously hard? Why can't just any chemical company jump in and start competing? Well, it's because the barrier to entry is deceptively, incredibly high. The answer really lies in a field called colloidal science. And what that is the incredibly complex chemistry of keeping billions and billions of these solid nanoparticles perfectly suspended in a liquid, and making sure they never ever clump together or settle at the bottom. Because if that colloidal chemistry is off by even a tiny bit, those particles will start to clump together. And the second they do, the whole batch of slurry becomes completely useless. It doesn't matter if it happens during manufacturing, or during shipping, or even while it's just sitting in storage at a chip factory. If it clumps, it's garbage. End of story. And that right there, that's the moat. That's the barrier. Achieving that perfect stable suspension requires decades of built-up knowledge and super specialized filtration and stabilization chemistry. It's a kind of mastery that you just can't buy or reverse engineer overnight. It absolutely has to be earned, the hard way.
Okay, so take a look at these two. How in the world are they connected? You've got Ajinomoto on one side, the MSG company, the stuff in your pantry. And then on the other, you have the absolute beast that's powering the entire AI revolution, an advanced GPU. It seems like there's no way, right? But believe it or not, one literally cannot function without the other.
So to really get this, we've got to go back in time. Let's jump back to the 90s. Tech is exploding, right? Chips are getting faster and more powerful at this insane rate. But all that progress, it was actually creating this huge hidden problem, a crisis really, in the very way these chips were being built. The whole issue was just scale.
As those CPUs got more and more powerful, the number of little tiny pins they needed to connect to everything else just went through the roof. We're talking from a few hundred in the 90s to thousands in the 2000s to today, where we're looking at tens of thousands of connections. It was a complete wiring nightmare, all happening on a scale you can't even see.
So the way they used to package these chips, it just completely hit a wall. They were using these liquid insulators to keep all the tiny wires from touching. But the problem was, this liquid stuff dried way too slow, and it was super uneven. The analogy here is perfect. It's like trying to build a skyscraper with concrete that just won't set right. The whole thing is about to fall apart.
And this whole mess, it all centered on one specific part, something called the chip substrate. The easiest way to think about it is like a super complex adapter. It's the bridge. It takes all those microscopic wires on the silicon chip itself and translates them or fans them out to the bigger connections on the motherboard that you can actually see. And that little bridge, that became the battleground where this whole tech crisis played out.
So who was going to solve this? Intel? IBM? Nope. The breakthrough didn't come from any of the tech giants you'd expect. It came from a food company. And they solved it using the exact same kind of chemistry they used to make your soup taste, well, tastier.
And here it is, the big reveal. See, Ajinomoto were and still are world experts in amino acid chemistry. That's their whole thing. So they took all that incredible knowledge, but instead of creating another flavor enhancer, they pivoted. They created a totally new material, a kind of solid thermosetting film that just so happened to be the perfect insulator for electronic.
And you can see right away why this was a total game changer. That old liquid stuff, slow, messy, full of defects, but this new Ajinomoto buildup film, they call it ABF, it was a miracle. We're talking perfect insulation, super durable, and it barely expanded when it got hot, which is absolutely crucial when you're packing circuits that close together. It was everything they needed. And the process for using it is just, it's so smart, it's elegant. You basically take a thin sheet of this ABF film, lay it down, use lasers to etch the tiny circuit pathways onto it, and then you just put another layer of film on top. And you do it again. And again, you're literally building this perfect 3D skyscraper of wiring, layer by tiny layer.
So think about it. What happens when your company invents the one perfect solution to a problem that's holding back the entire tech industry, and nobody else can figure out how to make it? Well, you get a monopoly. A very quiet but very powerful monopoly.
And I'm not exaggerating when I say monopoly. I mean, everybody uses this stuff. Your Intel Core processor, it's in there. An AMD Ryzen CPU, yep. Those incredibly powerful NVIDIA GPUs that are the engine of the AI boom, they absolutely depend on it. Pretty much any high-performance chip you can think of is built using Ajinomoto's film.
The sheer scale of this it's just hard to wrap your head around. When it comes to the specific kind of film needed for these top-tier chips, Ajinomoto doesn't just lead the market, they basically are the market. Look at this. We are talking a market share of something like 99%. It's unbelievable.
Okay, but here's the catch. Having just one company making something so critical, that's a huge risk. It's what they call a single point of failure. And when that single point of failure is part of the supply chain for the entire global tech industry, well, that's not just a risk. That's a massive global bottleneck waiting to happen. And that risk? It became very, very real during the pandemic. We all remember the global chip shortage, right? Couldn't get cars, couldn't get game consoles. Well, a huge hidden part of that crisis was the substrate shortage. At one point, the wait time to get these ABF substrates was over 50 weeks. Think about that. Almost an entire year just to get one little... So here's the thing you have to understand. The whole world was talking about a silicon shortage, but that wasn't the full story. A massive part of the crisis was actually a shortage of the packaging. The world had plenty of silicon wafers, but it didn't have enough of this special amino acid-based film to actually turn them into usable chips. And just when you think this story can't get any more relevant to today, well, think again. Because the AI boom that's happening right now, it's making this one humble ingredient more critical than it has ever been.
Why? Because AI chips are a different breed of animal altogether. They are physically enormous and unbelievably complex. A regular CPU might only need, say, a handful of these ABF layers. But a monster AI GPU, we're talking about needing these huge substrates with dozens and dozens of layers, all just to handle the insane amount of data that's constantly flowing through. And all of this leads to a pretty mind-blowing conclusion, one that comes straight from the source material in this. Ajinomoto, again, a food company, is now considered just as critical to the entire AI ecosystem as a company like TSMC that makes the chips or NVIDIA that designs them. They've become this quiet, completely essential giant of the tech world.
So what does a single speck of dust have in common with a leaky faucet? I know, it sounds like a weird riddle, right? But the answer? Well, the answer gets us right to the heart of two of the biggest, most fundamental challenges in all of modern technology. I'm talking about problems so big they could literally stop our digital world dead in its tracks.
Okay, so let's tackle that first problem, dust. Now, in the super clean world of making computer chips, a single microscopic speck of dust isn't just annoying, it's an existential threat. We're talking about something that can cause millions and millions of dollars of damage in an instant. And here's how that disaster unfolds. It's really a domino effect. So first, you have this blueprint for the chip. They call it a mask. Think of it like a stencil. Now imagine a single tiny dust particle lands on that stencil. Step 2. That particle blocks the special light they use for printing, this stuff called extreme ultraviolet light, or EUV. What happens next? Well, that tiny little shadow, that flaw, gets printed onto every single chip they make with that mask. And just like that, the entire production run is toast, destroyed. All because of one microscopic speck.
Okay, so how do you possibly solve that? I mean, you can't just slap a piece of glass over it because that super sensitive UV light would just get absorbed. Nope, the solution is something else entirely. It's called a pellicle. The best way to think about it is like a tiny, invisible trampoline that floats just above the blueprint. Any dust that falls just lands on the pellicle, not the blueprint itself. And because it's not in focus, the shadow it casts is so blurry that it doesn't get printed. It's a really clever idea, right? But actually making one of these things, well, that's an engineering nightmare. And here's exactly why it's a nightmare. A pellicle needs to be around 30 nanometers thick. Now, to give you some perspective, a single human hair is about 80,000 nanometers thick. So this thing, this pellicle, is more than 2,000 times thinner than a strand of your hair. Let that sink in for a second. It's practically nothing.
So this creates this just impossible set of demands for the material scientists. You need something that's almost unimaginably thin so all that precious UV light can get through. But it also has to be incredibly strong enough to handle insane heat and to survive being shaken around at incredible speeds. It's like asking for something to be both a piece of tissue paper and a sheet of steel at the same time. Honestly, it's a material that really shouldn't even exist.
And this is where our first hidden hero steps into the spotlight, a company called Mitsui Chemicals. This Japanese firm is, without a doubt, the world leader in making these impossible dust shields. They basically cornered the entire market. They're so good at it that without them, the mass production of the world's most advanced chips would just stop. It would grind to a halt. Their quiet dominance makes them one of the most important companies you've never heard.
Okay, so that's the dust shield. Now let's talk about that leaky faucet. We're about to go even smaller now. We're diving deep inside the billions and billions of transistors that are packed onto a single chip. We're moving from a physical shield down to a subatomic dam.
So every single transistor has what's called a gate. You can think of it like a faucet that turns the flow of electrons on and off. For a long time, the insulation for that gate, the part that stops the flow, was made of silicon oxide. But as we kept shrinking transistors, that insulating layer got thinner and thinner until it was just a few atoms thick. And at that point, a weird quantum physics thing starts to happen. Electrons just tunnel right through it. The faucet was leaking constantly. The fix? A totally new kind of material called a high-K dielectric. Basically, a much better insulator that could build a stronger dam and stop those pesky electrons from leaking out.
But how on earth do you build a dam that's only a few atoms thick? You obviously can't just pour it on there. No, the way they do it is incredible. They build it one single atomic layer at a time. And they do this using things called chemical precursors. These are super complex chemical compounds delivered as a gas that basically paint themselves onto the chip's surface, atom by atom, building up this perfect, flawless, leak-proof barrier.
And this quote right here just nails their whole business model. This isn't about making tons and tons of stuff. It's the complete opposite. It's about producing these tiny, perfect little batches of chemicals that are just insanely difficult to synthesize. We are talking about a level of purity, of complexity, that almost nobody else on the planet can pull off.
And that brings us to our second hidden hero, Chemical Laboratories. This is another niche Japanese company, and they specialize in making these exact chemical precursors. You can think of them as the master chefs of the atomic world. They're cooking up the special ingredients that are absolutely essential to keep modern chips from leaking, overheating, and failing.
And because they're so hyper-specialized, the biggest chip makers in the world are completely dependent on their secret recipe. All right, so we've got one company making these impossible shields and another one cooking up atomic scale ingredients. Two totally different things, right? But what connects them is this really important idea, a concept that's absolutely crucial to understanding our modern world, the technological choke point.
So what's a choke point? Well, it's what happens when a company gets so good, so specialized at doing one tiny but completely essential thing that there's just no one else who can do it. There's no backup plan. And suddenly, the entire multi-trillion-dollar tech industry depends on this one company's unique, often secret know-how. If they succeed, we all succeed. But if they fail, it could be a global catastrophe.
And this table here just lays it all out perfectly. You've got the dust shield on one side, the leak stopper on the other. Mitsui Chemicals solves a physical problem, particle contamination, with their pellicles, and that makes mass production even possible. Then you have Chemical Labs solving a quantum problem, electron tunneling, with their chemical precursors, which stops chips from frying themselves. Two completely different worlds, two completely different problems, both solved by these obscure masters of their craft.
Yep, a few ultra-pure chemicals that you've never heard of. It's kind of wild, but our entire modern world runs on a silent, steady flow of these materials. So what happens when that flow gets threatened? Well, that is where our story really begins. So, how does this dependency on something invisible become such a massive risk? It all comes down to this really powerful concept called weaponized interdependence. Okay, that sounds super academic, I know, but the idea is actually pretty simple. Imagine everyone in the world needs one specific thing, and only one place makes it. Well, that one place suddenly has a ton of power, right? That dependency can be used like a weapon in a trade fight, or it can become this huge single point of failure if something just goes wrong. And this slide really gets to the heart of it. We all know the visible giants of tech, Samsung, TSMC, Intel, they're household names. But the real power, the very foundation everything is built on, lies with these invisible titans, companies like Stella Chemify or Merita Chemical. They're the ones making the absolutely irreplaceable stuff that the giants need to even exist. And look, this isn't just some abstract theory. Back in 2019, this risk became a reality in a huge way during a really tense dispute between Japan and South Korea. So let's just walk through what happened. It all started with these deep historical grievances bubbling under the surface. Then, boom, July 2019, Japan suddenly cuts off exports of these critical chemicals. The impact was immediate. We're talking a full-blown production crisis for South Korean chipmakers. And their response? They had to pour billions into creating their own domestic supply chain, basically from scratch. It was a perfect example of how geopolitics could be used to just throttle a nation's most important industry. These were the three materials that were targeted. You had fluorinated polyamide, photoresist, and the real killer, high-purity hydrogen fluoride, or HPHF. This last one was the most crippling blow because it is absolutely essential for cleaning and etching the silicon wafers that, become our computer chips. No HPHF, no chips, it's that simple. And this chart just lays it all out, doesn't it? At the time, Japanese companies produced almost 90% of the super-duper pure HPHF that companies like Samsung needed. It was a near monopoly. Japan basically controlled the tap, and with one political decision, they just turned it off for their rival. Now, you might be thinking, okay, so why couldn't South Korea just buy it from somewhere else? And that's the crucial point. It's all about purity. In advanced chipmaking, even the tiniest deviation, we are talking about impurities measured in parts per billion, can destroy an entire multi-billion-dollar production line. You can't just switch suppliers like you're buying a different brand of coffee. The chemical recipe has to be absolutely perfect. But a disruption doesn't always come from some deliberate political move. As we're about to see, sometimes the threat comes from a completely different direction. In this case, environmental regulation. Get this number in your head, 80%. That's how much of the world's supply of essential semiconductor coolants came from a single 3M factory in Belgium. One factory was cooling the machines for pretty much the entire global chip industry. That's insane. And then, in 2022, the unthinkable happened. It started with a shutdown order from the Belgian government because of environmental concerns about PFAS chemicals. That immediately cut off 80% of the world's coolant supply. A little while later, giants like TSMC and Intel were staring down the barrel of imminent shortages. The world suddenly woke up to a brand new vulnerability, the green choke point. What this whole episode made crystal clear is that the tech industry's insatiable need for these often toxic, exotic chemicals is on a direct collision course with the global push for stronger environmental protections. And this isn't some one-time fluke. It is a persistent, growing threat to the whole system. So, what do these two stories, one about politics, one about pollution, really tell us about our global system? Well, they reveal a shocking level of fragility that's just hidden right below the surface of our super-connected world. Just think about it for a second. A global tech shutdown could be triggered by a local regulatory ruling in Belgium, or a political squabble between Japan and Korea. But it could just as easily be a natural disaster, like an earthquake in Tokyo, or just a random factory fire in Gumi, South Korea. The entire digital world we rely on depends on none of these things happening in a few very specific, vulnerable places. And that really brings us to the core takeaway here. The stability of our future, our AI, our phones, our economies, it doesn't just rest on the shoulders of those famous tech giants. It depends completely on the silent, uninterrupted flow of materials from companies most of us will never, ever know exist.
A company that's almost totally invisible to most of us, that builds the machines that build the chips. Today, we're going to pull back the curtain on that company, Applied Materials.
And let me tell you, that is not an exaggeration. We're talking about a process that takes months, involves hundreds of unbelievably precise steps, and all happens inside rooms that are thousands of times cleaner than an operating room. The scale of it is it's hard to even wrap your head around. And that, right there, brings us to our main subject. The easiest way to think about it is like this. If the entire semiconductor industry is a super high-tech frontier town, then Applied Materials, well, they're the general store. They sell all the most critical, must-have equipment to everyone in town. Now, this isn't some small-town shop, obviously. Applied Materials, or AMAT, if you're looking at the stock ticker, is the undisputed heavyweight champion in this space. While some of their competitors might focus on just one specific tool, AMAT does it all. They make tools for pretty much every step of the process, which gives them this incredible bird's-eye view of the entire industry. And the numbers? Well, they really tell the story of just how massive they are. We're talking a market cap north of $200 billion. They pulled in over $26 billion in revenue just last year. And get this, they command somewhere between 19 and 21% of the entire global market for this equipment. They are a true behemoth.
Okay, so let's zoom in a bit. Forget the business side for a second, and let's talk tech. What do they actually do? Because it's not just about building big, fancy machines. It's about engineering with the fundamental building blocks of our universe.
At the heart of everything they do is a process called deposition. Seriously, the best way to think of it is like 3D printing with atoms. It's the art of adding impossibly thin layers of different materials onto a silicon wafer, one after another, to build up the chip's incredibly complex 3D architecture.
And this is where their mastery really becomes clear. It's not a one-size-fits-all process. When chip makers need to create tiny metal wires, AMAT's tools use something called PVD. For insulating layers, it's CVD. But for the most critical, most mind-bogglingly precise parts, they use ALD, atomic layer deposition. That is literally building the chip one single layer of atoms at a time. The precision is insane, because at this scale, one stray atom can ruin the whole thing. You know, this kind of technological dominance doesn't just appear overnight. It's been built up over decades on the back of these legendary equipment platforms that have really set the standard for the entire industry.
You can actually see the evolution right here. It all started back in 1990 with the Endura platform, which just totally dominated PVD. Then came the Centura, another absolute workhorse. And now, to meet the crazy demands of the AI era, they've introduced the intelligent Vistara platform. Each one of these was a massive leap forward.
And that first one, the Endura, was pure genius. Think about it, a factory within a factory. Inside the machine, robotic arms moved the silicon wafers between different chambers to perform different steps, but the wafer never leaves the perfect vacuum. Now, why does that matter so much? Because at the nanoscale, even a tiny bit of exposure to air can create an oxide film that instantly ruins a connection. The Endura solved that problem. It was a game changer.
But, you know, the challenges of today, especially with AI chips becoming so complex, they demand a totally new way of thinking. And that brings us to their latest creation, the Vistera revolution.
This comparison right here, it just gets to the heart of the whole change. The old way of thinking was that these machines were basically just very, very sophisticated tanks for chemical reactions. But the new model? Now, they're thought of as data-generating edge devices. That's a fundamental shift. The tool isn't just a dumb machine doing a job anymore, it's a smart machine that's learning while it works.
So what makes this Vistara platform so revolutionary? Well, for one, it's incredibly flexible. It can combine all sorts of different processes in one system. But the real secret sauce is its intelligence. It's absolutely packed with thousands of sensors that are constantly monitoring every tiny variable, feeding an insane amount of data to an AI platform. This allows the machine to optimize itself on the fly and catch tiny problems before they become big ones.
So all of this amazing technology creates a ridiculously powerful business advantage. Let's zoom back out and talk about the moat that protects Applied Materials' kingdom from invaders.
It starts with this number, $3.23 billion. That is what they are planning to spend on research and development in a single year. Just trying to match that kind of spending is a huge barrier for any company that wants to compete.
But here's the thing. The real moat isn't just the money, it's the data. See, to truly compete with Applied Materials, it's not enough to build a better machine. You'd somehow have to replicate decades of proprietary, hard-won materials science data that their machines have collected. That knowledge, that's their real competitive advantage. You just can't buy them. And this is what it all adds up to. Just incredible financial strength. A gross margin of almost 48% means they make a ton of profit on every tool they sell. And a return on equity over 34%, that shows they are amazingly efficient at using their capital to generate even more profits. It's really the picture of a company at the absolute top of its game.
So to really wrap our heads around what Lam Research actually does, we need a really simple but I think powerful analogy. You see, when it comes to making computer chips, there are basically two ways you can go about it. On one hand, you've got companies that are kind of like painters. They add layers of different materials onto a silicon canvas. But Lam Research, they're the sculptor. Their entire job is to precisely, meticulously remove material, carving away at the atomic level to create these incredibly intricate, three-dimensional canyons and pillars that actually make a modern chip work.
And this unique role, being the master sculptor for the entire semiconductor industry, has made them the absolute, undisputed global leader in a process called etching. Now, this isn't just some minor step in manufacturing. It's a foundational technique that our modern world of electronics simply could not exist without. But you know, being the best sculptor in the world isn't a title you get to keep by standing still. In fact, the job has gotten exponentially harder. The challenge Lam faces now isn't just about being precise, it's about navigating what feels like truly impossible geometry.
For the longest time, chips were mostly flat, like a map laid out on a table. But eventually, you just run out of room, right? So to get more power and more memory, the industry had to start building up. They moved from those flat 2D designs to these complex vertical 3D structures. And as you can imagine, when you start building vertically, the sculptor's job changes completely.
Just take the memory in your phone or your computer's solid-state drive. That's not a single-story building anymore. It's a skyscraper. We're talking about memory cells stacked on top of each other, sometimes over 100 layers high. And to make the whole thing work, you have to carve these perfectly straight, microscopic holes. Think of them like elevator shafts, all the way from the penthouse down to the basement.
This analogy just perfectly captures how insane the level of precision we're talking about really is. Just think about that. If that hole, that etched shaft, tilts by even a fraction of a single degree, it misses the dinner plate in the basement, and the entire multi-million-dollar device is completely useless. It's an all-or-nothing game at a scale that's hard to even comprehend.
So that leads to the big question. How on earth do you do that? I mean, you can't just use a tiny drill bit. You need tools that operate right on the very edge of what physics allows. Lam's primary tool, their main chisel, if you will, is something called high-density plasma. You can basically think of it as a particle cannon. It takes the gas, superheats it, charges it up electrically, and then fires these particles, called ions, straight down into the silicon wafer. It's this controlled blast that carves those impossibly deep and narrow holes with incredible force and direction.
But here's where it gets really clever, because there's a tricky physics problem. As you're blasting deeper, you can get unwanted chemical reactions on the sides of the hole which can cause it to curve or bow outwards, and that's a failure. So,
Lam's solution is just brilliant. They pioneered cryogenic etching. They literally freeze the wafer to ultra-low temperatures while they're carving it. This stops those side reactions cold, allowing the particle cannon to keep carving a perfectly straight path.
And for the next generation of transistors, the problem gets even more delicate. We're talking about removing sacrificial material from between these incredibly thin silicon nanosheets without damaging them. For that, they use a process that's less like carving and more like chemical magic. They use these special chemistries to dissolve only the material they want to remove with Angstrom-Level Precision. That's the size of a single atom, while leaving the critical structures right next to it completely untouched.
Okay, but having the world's best, most precise tools isn't the whole story. In the multi-billion-dollar world of chip manufacturing, the sculptor's workshop also has to be incredibly smart and incredibly efficient. And get this, Lam's latest platform called Sense.i is a total game changer. It delivers a massive 50% improvement in what they call etch output density. Now, in a chip factory, where every single square foot of floor space is worth an absolute fortune, boosting your productivity by 50%, that's just an enormous, enormous advantage.
And this platform isn't just fast, it's smart. You could almost call it self-aware. It's packed with sensors, it uses machine learning to chew through tons of data in real time, and it can actually calibrate itself on the fly. It can predict problems before they even happen, which means fewer errors, less downtime, and a lot less need for human intervention.
So, what does this all add up to? This complete mastery of atomic-level sculpting, combined with the super smart workshop, what does it actually mean for the company and for the rest of us?
Well, for starters, it means market dominance. Lam Research controls a staggering 45% of the entire global market for this kind of etching equipment. I mean, that's not just a lead, that's a massive competitive moat around their business built by solving these impossible physics problems that others just can't.
And that technical leadership? Well, it prints money. We're talking about a return on equity of over 54% and net profit margins that can hit 30%. These aren't just good numbers. They're the kind of incredible financial results you get when you are absolutely essential to an entire industry.
And they are not resting on their laurels, not for a second. The company is pouring nearly $2 billion back into research and development in a single year. That's a massive bet they're making to stay ahead of the curve and to solve the next generation of impossible problems.
And here's the real bottom line. Here's why all of this matters to you and me. This atomic level sculpting is the fundamental reason we have the hardware that powers the AI revolution. Things like high bandwidth memory that are needed to train huge models, or the ultra-fast enterprise storage that feeds them all that data. None of it happens without this exact kind of 3D etching mastery.
See, when you're working with billions of microscopic transistors, all crammed onto a tiny piece of silicon, there is absolutely zero room for error. I mean, a single atom out of place can make a multi-million-dollar chip completely worthless. The stakes are just unbelievably high. So you gotta ask, right? In this crazy high-stakes game of microscopic precision, who's the referee? Who's the guardian, making sure the very building blocks of our entire digital world are absolutely 100% flawless? Well, that guardian is a company you've probably never even heard of, but it's one that is absolutely essential to, well, everything. That company is KLA Corporation. You can really think of them as the unsung heroes of the entire semiconductor industry. Okay, so here's the key thing to get. Companies like TSMC, Intel, they might be the brilliant architects, the master builders of the chip. But KLA, they provide the super advanced eyes and rulers to guarantee that what got built actually works. They are the quality control inspectors for the atomic age. To really get why KLA is such a big deal, we need to talk about money, a lot of money. It all comes down to this one singular, incredibly important metric. And that magic word is yield. It's pretty simple, actually. It's just the percentage of good working chips you get from each big silicon wafer. So if you bake a tray of cookies and only half of them are edible, you've got a 50% yield. And trust me, the entire semiconductor industry lives and dies by this number. Okay, but here's where it gets really, really tough. When a company is rolling out a brand new cutting-edge chip, those first yields, they can be a total disaster. We're talking single digits. That means over 90% of the chips on that wafer are just super expensive garbage. And this is where the money is, people. For a big chip maker, improving that yield by just 1% can translate to tens of millions of dollars in pure profit. That is the massive, multi-million-dollar problem KLA was born to solve. So how in the world do they do it? How do you spot a flaw that's smaller than a virus? Well, it turns out KLA has pretty much mastered two incredible ways of seeing the invisible. And they do it with two very different tools. One uses light, and the other uses electrons. Okay, so think of it like this. On one hand, you've got optical inspection. This is the fab's radar. It blasts the wafer with light that's brighter than the sun, scanning the whole thing in about an hour. It's great for finding bigger stuff on the surface. But for the really tiny hidden electrical faults, you need a microscope. And that's where E-beam comes in. It uses a beam of electrons to see things light just can't. The only problem? It's about 1,000 times slow. So right there, you've got this classic trade-off, don't you? Speed versus precision. A fast radar or a slow, powerful microscope. But this is where KLA's real genius kicks in. They don't choose one or the other. They combine them into this brilliant hybrid strategy. Check this out. Here's how the magic happens. First, that super fast optical radar scans the entire wafer. Then, KLA's incredibly smart software analyzes that scan and maps out any potential trouble spots or hotspots. And only then do they send in the super precise E-beam microscope to do a deep dive analysis on just those specific coordinates. It's the absolute best of both worlds. And because KLA has mastered both the hardware and the software, it's a huge barrier to any competitor. But it's not just about spotting mistakes, you know? KLA is also the master of what's called metrology, which is just the science of measurement. But we're talking about measuring things with sub-angstrom accuracy. That's a fraction of the width of a single atom. It's just mind-boggling. Their AI is so advanced, it can even tell the difference between a killer defect that will ruin a chip and a harmless little nuisance defect. This is the kind of precision that makes future tech, like next-gen transistors, even possible. Okay, so all this incredible tech, it's not just cool for engineers, it's an absolutely killer business model. Let's look at how being the guardian of perfection actually pays the bills. Think about it. When your gear is the only thing that can solve that multi-million-dollar yield problem we just talked about, guess what? You get some serious pricing power. And you can see it right in their gross margins, which are consistently over 60%. That is way, way higher than their peers. When your product is that essential, you can charge what it's worth. And they are not sitting still, not for a second. To keep this incredible lead, KLA is projected to spend a jaw-dropping $1.4 billion on research and development in a single year. That's just the price you have to pay to stay on top when the finish line is measured in atoms. And that massive R&D spending, that's not just a line item on a budget. It's a giant, uncrossable moat around their castle. It makes sure their technological eyes are always sharp enough for tomorrow's chips, making it pretty much impossible for anyone else to even try to catch up. So here's the wild part. The same secret sauce that lets your phone last all day on a single charge, that's now being used to solve one of the biggest challenges in technology today. Which brings us to this central question. How on earth is your phone's DNA powering the entire AI revolution? You know, for the longest time, the world of computer chips was pretty simple. Think of it like two massive kingdoms, two empires, that just didn't mess with each other. They each had their own territory, their own rules, and for decades, they were happy to stay that way. To really get what's happening, we need to talk about a company called ARM. Now, ARM is super interesting because they don't actually build the physical chips. They're the architects. They design the blueprint, the fundamental language that a processor understands. It's called an instruction set architecture, or an ISA. And because they just license these blueprints out, their language ended up, well, everywhere. It's literally the most common chip language in history. And this is where you can really see those two kingdoms clearly. On one side, you've got ARM. Their whole philosophy, their RISC architecture, was all about one thing: sipping power, energy efficiency. That's why they were the no-brainer choice for anything with a battery, like our phones. But then you had the other kingdom, the x86 fortress, ruled by giants like Intel and AMD. Their approach? Raw, brute force performance. That made them the undisputed kings of anything you plug into a wall. Servers, desktops, you name it. And this balance of power, it worked for a really, really long time. But then, something big happened. A huge shift in how we all compute started to put a crack in the walls of that x86 fortress. And that shift was the rise of the cloud. All of a sudden, if you're a company running millions of servers 24/7, raw speed isn't your only problem anymore. You've got a new enemy: a really expensive one, your electricity bill. The sheer power draw from that x86 Fortress was becoming a gigantic, unsustainable headache. So this forced the giants of the cloud, we're talking the hyperscalers like Amazon, Microsoft, and Google, to completely change how they thought about things. They developed a brand new obsession: performance per watt. It's a simple idea, really. How much bang can I get for my electrical buck? And just like that, the definition of a powerful chip changed overnight. It wasn't just about being the fastest, it was about being the most efficient. And right there, that's the moment ARM, the humble king of power-sipping phone chips, saw its opening. Its whole business model, just licensing out the blueprints, suddenly looked like a genius move. It gave these cloud giants a totally new weapon to fight their massive energy problem.
So here's the playbook they all ran, and it was brilliant. Step 1, license ARM's special data center platform, which is called Neoverse. Step 2, use those blueprints to design their own custom chips, tweaked perfectly for exactly what they need to do in their clouds. And the best part, step 3, they completely cut out the middleman, the traditional chip vendors, and all the extra costs that came with.
And boom, the results? A whole new wave of custom-built chips. Amazon came out with Graviton, Google rolled out Axion, Microsoft made Cobalt. All of a sudden, you've got this new army of custom silicon, all speaking ARM's language, marching right up to the gates of that old x86 Fortress. Now, right as this whole invasion was kicking off, another tidal wave was building, something that would take ARM's efficiency from being a nice little perk and turn it into an absolute necessity. And you know what I'm talking about, the AI boom. Look, the amount of power it takes to train and run these new AI models is just mind-boggling. It's so big, in fact, that ARM's own CEO, René Haas, put out this really stark warning. He basically said that if we don't switch to more efficient chips, AI is on track to cause a legitimate energy crisis. I mean, just take a second and let that number really sink in. A quarter of the entire US power grid, just for AI. It's insane. And this massive energy problem, it's probably the single biggest thing pushing ARM forward. It's creating this desperate, urgent need for exactly what ARM has been doing all along: maximum performance for minimum power.
And hey, if you're thinking, okay, but can ARM really hang with the big dogs for serious performance? Well, here's all the proof you need. Look at NVIDIA. They are the undisputed kings of AI hardware, right? For their own monster AI supercomputer chip, the Grace CPU, what architecture did they choose to build it on? Yep, ARM.
Okay, so this all sounds great for ARM, but an ambitious plan to take over the data center costs a lot of money. So where's that cash coming from? Well, it turns out their business model is just as smart as their tech. It's pretty simple, really. ARM gets paid through licensing fees and royalties on every single chip that uses their design. And their newest architecture, the V9, which is built specifically for the data center and AI, it comes with royalty rates that are about double what they got for the older stuff in our phones. So more powerful chips for their customers means way more money for ARM. And what are they doing with all that extra cash? They're plowing it right back into the war effort. In 2024 alone, their spending on R&D shot up by almost 75% to around $2 billion. That's all going into making sure their Neoverse platform doesn't just compete with Intel and AMD, but beats them. And that brings us to ARM's endgame here. Their goal isn't just to get a piece of the pie. They want to conquer the whole kingdom. They have set this absolutely wild goal to grab 50% of the entire data center CPU market. The same market that, just a few years ago, everyone thought was an untouchable fortress. Today, we're going to pull back that curtain and look at the software that builds our hardware. And it all starts with a problem of just mind-boggling scale. Right, to really wrap your head around the challenge, let's just start with a number. A single modern chip can have over 50 billion transistors crammed onto a piece of silicon smaller than your fingernail. That's more transistors than there are people on the entire planet. The scale is it's almost impossible to comprehend. And the money involved? Well, it's just as massive. Creating the master template for one of these chips, it's called a mask set, can cost over $500 million. And if there's one tiny microscopic bug in that design, all of that money, it's just gone. Poof, incinerated. And oh yeah, your product is now delayed for months. So, that leads us to the big question, right? How on earth do you design something with billions of parts where a single mistake costs $500 million and you have to get it right the very first time? The answer, I can tell you, is not just human brain power. Not anymore. The solution is this very special category of software. It's the essential bridge that takes an idea from an engineer's brain and turns it into a physical chip. It's called Electronic Design Automation, or EDA. And frankly, it's the only reason we can build these incredible things at all. So what exactly is EDA? Well, imagine it's the ultimate blueprint and simulator for electronics, all rolled into one. This software translates an engineer's abstract ideas into a physical layout of billions of transistors. It figures out how to wire them all together, and, this is the most important part, it runs virtual tests to make sure the chip actually works before a single cent is spent on manufacturing. Now, here's where it gets really interesting. You'd think a market this critical, this essential, would be full of companies fighting for a piece of the pie. But it's not. It's basically a duopoly. Just two companies, Synopsys and Cadence Design Systems, control about 75% of the entire landscape. And these two giants, they've historically ruled very different kingdoms. Think of it like this. Synopsys is the master of the digital side of things, the pure logic, the ones and zeros, the massive puzzle of placing and connecting all those billions of transistors. Cadence, on the other hand, is the king of analog, the really tricky circuits that have to deal with real-world signals like sound and radio waves and power. They built a bridge from our digital devices to physical reality. For a long, long time, the main challenge was basically a digital logic puzzle. A huge one, but still a puzzle. But as we keep cramming more and more transistors into smaller and smaller spaces, a new, much more complicated problem has shown up. The physical world itself is starting to fight back. And this quote just says it all. A chip design can be logically perfect, a total masterpiece of digital design. But if it gets so hot that it melts, or if it literally warps under physical stress, or if its own magnetic fields interfere with each other, it's a total failure. Logic just isn't enough anymore. And this has kicked off nothing short of an arms race between the two big guys. The whole definition of chip design is changing. It's expanding way beyond just circuits and into the super complex world of multi-physics simulation. It's not just about placing transistors anymore, it's about simulating the entire physical reality of the system. So Synopsys made this enormous move. They spent $35 billion to buy Ansys, a company that's a leader in physical simulation. I'm talking about the kind of software that's used to stress test jet engines. The goal? To create a digital twin of the entire system. It's like building a perfect virtual copy of a smartphone, so you can see exactly how the chip is going to heat up and perform inside it long before you ever build a real. And of course, Cadence responded right away. They went out and acquired companies like Beta CAE for over $1 billion, all to build up their own tools to simulate physical stress and fluid dynamics. The race is on to see who can build the most complete, most accurate virtual model of a chip's life in the messy, real world. But there's another force at play here. The complexity of these chips is just growing so fast that it's starting to outrun the supply of human engineers. We're hitting a wall where even the absolute best human engineers just can't explore every single possibility. And the answer to that problem is AI. Both companies have developed these incredibly powerful AI design partners. Synopsys has DSO.ai and Cadence has Cerebrus. They both use a technique called reinforcement learning. You can think of it like teaching an AI to play a video game. It tries a design, it gets a score based on how well it did, and it learns from its mistakes to try a better design next time. So while a human might test 10 different layouts, the AI can run through thousands overnight, finding solutions we would just never think of. And the results are, well, they're staggering. Giving an engineer one of these AI partners doesn't just help a little bit, it can triple their productivity. This is not a small step forward. It is a complete revolution in how we design technology. And it goes beyond just speed. These AI tools are finding really clever, non-intuitive solutions that human engineers would probably never even try. And these solutions are leading to chips that are 10 to 20% more power efficient. In a world of battery-powered everything, that is a huge advantage. So, how do these companies afford to stay on the absolute cutting edge of physics, AI, and computing? Well, it all comes down to a business model that is just as powerful and just as well designed as the software they create. A huge part of the answer is their massive commitment to innovation. Both Synopsys and Cadence pour about 35% of their revenue right back into research and development. Now, that number is way higher than most hardware companies, and it's exactly how they maintain that deep technological moat around their businesses. Their whole model is just built for resilience. See, they sell software on a subscription basis, which gives them this really stable, recurring revenue. And that shields them from the wild ups and downs of the hardware manufacturing industry, letting them consistently fund that next great leap forward year after year.
So back in the day, a company would literally design every single part of a chip themselves. But as things got more and more complex, that just became impossible. Today, the approach is completely different. You think of a chip less like a single sculpture and more like a complex puzzle made of pre-designed interlocking pieces. And this is what we call the IP economy.
So, what is this IP economy, really? How does this modern chip puzzle actually fit together? Let's peel back the layers and see what's going on.
Okay, first things first. Semiconductor IP isn't a physical thing you can hold. It's more like a highly sophisticated blueprint. It's a pre-verified, reusable design for one part of a chip that handles a standard but incredibly complex job. By using these pre-made blocks for stuff like Wi-Fi or memory control, companies can skip reinventing the wheel and get their products out the door way faster. And this is where the real magic happens. It means a company like Google can pour all of its brainpower into its Tensor AI cores. That's their secret sauce. They don't have to waste time and energy designing a basic USB controller. No way! They just buy that puzzle piece from a specialist. It's kind of like a master chef sourcing the absolute best ingredients so they can focus on creating their signature dish.
All right, so who are these specialists, these master ingredient suppliers? Well, let's start with a company that's tackling one of the biggest bottlenecks in all of AI, the memory problem.
Think about it for a second. You can have the fastest, most powerful AI processor in the world, but if you can't feed it data fast enough, what does it do? It just sits there, waiting. It's a massive traffic jam on the information superhighway. So how do you solve for that?
This is where a company called Rambus comes in. They are the absolute masters of the physical interfaces for the super fast memory that AI just gobbles up. We're talking about stuff like DDR5 for servers and high bandwidth memory, or HBM, where the memory is literally stacked right next to the processor for insane speeds. Rambus basically designs the critical high-speed bridge between the processor and the memory.
And one of their key pieces of tech is the registered clock driver, or RCD. See, as speeds get faster and faster, sending a clean electrical signal becomes incredibly difficult. Imagine trying to have a clear conversation in the middle of a hurricane. The RCD is this tiny, specialized chip that acts like a noise-canceling microphone. It cleans up all the signals to make sure there's zero data corruption. It is absolutely essential. And get this, their market position is just incredible. Rambus controls a staggering 45% of this critical RCD market. You heard that right. That means for almost half of all the high-speed memory being put into data centers all over the world, Rambus is the company making sure it actually works. That is some serious influence. Which leads to this brilliant business model. As every single data center on the planet rushes to upgrade to faster memory to power AI, they are, for all intents and purposes, paying a toll to Rambus. Because their tech is so baked into the industry standards, it's just a non-negotiable step on that road to more powerful AI. Okay, so Rambus helps get data from the memory to the chip. Great, but what about moving data between different chips, or even inside a single, massive chip? Well, that brings us to our next unseen architect, a company called Alphawave Semi. Alphawave is a specialist in something called SerDes. Now, the best way to think about a SerDes block is like the main gateway for a chip. It's the on-ramp and the off-ramp. It takes all the parallel data flowing inside the chip, kind of like a multi-lane highway, and funnels it down or serializes it into a single super high-speed lane to be blasted out. And then it does the exact reverse for all the data coming in.
And when I say blinding speeds, I mean it. We are talking up to 224 gigabits per second, per lane. To put that in perspective for you, that is fast enough to download a full-length 4K movie in well under a second. It is the essential data superhighway that connects our entire modern computing world. Now, here's where Alphawave's role becomes even more critical. You see, we're hitting the absolute physical limits of how big we can make a single piece of silicon. The bigger the chip, the more likely it is to have tiny manufacturing defects, which just tanks your yields and makes the costs go through the roof. The solution? Stop trying to build one giant monolithic chip. Instead, the entire industry is moving to what's called a chiplet model. You break the design up into smaller, more efficient, and easier to make chiplets. The problem is, you now have to connect them all so they act like one giant chip. And that's exactly where Alphawave's IP comes in. They provide the ultra-high-speed links that basically act as the central nervous system for this new generation of supercomputers.
So what does all this really mean? Well, it points to something incredibly important. This isn't just about a few clever companies finding a niche. It's about a deeply interconnected ecosystem where even the biggest giants, the biggest names you can think of, absolutely depend on these specialists. It's a story of symbiosis.
I mean, look at a chip foundry like TSMC. They physically manufacture the world's most advanced silicon. They can have the best process technology on the entire planet, but they can't sell those services if nobody can design chips for it. It's like having the world's most advanced oven but having 0 recipes. These IP companies, they provide the proven, ready-to-go recipes.
And if you want proof, look no further than this. TSMC, arguably the most important manufacturer in the world, named Alphawave its Partner of the Year. Now, this isn't just some nice pat on the back. This is a public declaration of just how deeply interdependent they are. The manufacturing giant needs the connectivity specialist to make their most advanced products a reality. So the next time you see some incredible new advance in artificial intelligence, just remember that the entire glittering AI edifice, all of it, is built upon the foundational and often invisible work of these unseen architects. Which, of course, leads to one last question.
You know, every time you pick up your phone or sit down at your computer, you're tapping into this hidden world of just unimaginable complexity. But what's really wild is that this entire world is built on a foundation of forced cooperation. So today, we're going to pull back the curtain and show you how one single tiny change in chip design created this unbreakable chain linking the fates of the biggest names in tech. And it all started with a problem that sounds pretty simple. It all boils down to a question we can all understand. How do you solve a traffic jam? We've all been there, right? But in this case, the traffic jam is happening on a microscopic scale, inside the very heart of our gadgets, and it's literally holding back the future of computing. So to really get the solution, you've got to understand the problem. Think of it like this. Traditionally, all the wires, the ones for power and the ones for data, are just crammed together on the front of the chip. They're all fighting for space. It's a total bottleneck. The brilliant idea? Just move the power wires to the back of the chip. It's like building a brand new superhighway just for electricity, which clears up all that traffic and frees up a ton of space for data to move way, way fast. Now, this revolutionary technique, it has a name, the Backside Power Delivery Network, or BSPDN for short. And this isn't some far-off science fiction, okay? This is set to be adopted in the next generation of chips, coming around 2025 or 2026. But, and this is the whole point, making this one change isn't as simple as it sounds, not even close. It sets off a massive industry-wide chain reaction. See, moving those wires from the front to the back, it triggers this incredible cascade, this huge domino effect across the entire industry. You can't just tell the factory to flip the chip over. No way. First, you have to completely redesign the chip's fundamental blueprints. Then, you need all new software just to create those blueprints. After that, you need new factory tools to physically build this thing. And finally, how in the world do you check your work when the most critical new parts are now buried deep inside the silicon? Well, you need entirely new ways to see. So let's break down each step of this incredible process. So the very first domino to fall is the blueprint itself. And we're not talking about a small tweak here. This is a fundamental rewrite of the rules of chip design, and it all starts with companies like ARM, Synopsys, and Cadence. Let's start with ARM. You can think of them as the architect. They designed the fundamental building blocks of a chip. With BSPDN, they had to completely re-architect these blocks to accept power from below instead of from above, something they've never ever had to do before. But okay, having a new design is one thing. You need the software to actually turn it into a reality. That's where Synopsys and Cadence, the tool makers, come in. Their software had to be rewritten from the ground up to handle this new two-sided world. And on top of all that, burying power lines totally changes how heat moves around, creating all these new thermal challenges that required brand new simulation tools to figure out. Okay, so the digital blueprint is done. Now for the really hard part. We're moving from the digital world to the factory floor to see how this thing actually gets built. This is the physical puzzle, and it's where companies like Lam Research and Applied Materials have to step up.
So how do you get the power from that new backside superhighway to the transistors waiting on the front? The answer is you drill. You drill these microscopic tunnels called through-silicon vias, or TSVs, straight through the silicon wafer to connect both sides. I want you to imagine drilling a hole through a skyscraper that's only a few inches wide, all without disturbing a single person inside. That is the kind of scale we are talking about. It's mind-boggling.
And making these holes, well, that's a job for a nanosurgeon. Lam Research is the company that builds these incredibly precise etching tools. They act like a microscopic scalpel, drilling these impossibly tiny, deep and narrow holes with perfect accuracy, all without damaging any of the fragile transistors that are already sitting on the front side. The level of precision needed is just staggering.
Right, so once Lam Research drills that perfect hole, you've got to fill it up. It has to be filled with a conductive metal, like tungsten, so it can actually carry the electricity. And this is where Applied Materials comes into the picture. It's their job to fill these microscopic tunnels perfectly, from the very bottom to the very top.
And when I say perfectly, I mean it. The margin for error is literally zero. This quote says everything. If there is a single air pocket in the via, the chip will fail. Just one microscopic bubble of air means the connection is bad. Resistance skyrockets, and the entire multi-million-dollar chip becomes a completely worthless piece of scrap. The work Applied Materials does is the razor-thin line between a breakthrough and a total disaster. Okay, so the chip is designed, it's drilled, and it's filled. We're done, right? Ha, not even close. There's one last giant hurdle to overcome. How do you even know if you did it right? This is the inspection problem, and it's KLA's challenge to solve. I mean, just think about it for a second. All of those critical new power connections, the things that make this whole idea work, are now buried deep inside the silicon wafer. You can't see them with a normal microscope. It's impossible. For the first time ever, the factory's flying completely blind, unable to see the most important new feature of the chip they just built. So KLA basically has to give the entire industry a form of X-ray vision. They've developed completely new inspection techniques using things like acoustic imaging and high-voltage electron beams that can literally see through the silicon. Their whole goal is to verify that those backside power lines and those tiny vias line up perfectly with the transistors on the front. Without KLA's eyes, no one could ever ship a BSPDN chip with any confidence that it actually worked.
So let's bring this all together. Let's pull back and look at the big picture. What we've just walked through is a perfect example of what we're calling the unbreakable chain. It's a story of forced cooperation, plain and simple. When you look at it like this, you can see the whole ecosystem laid out so clearly. It starts with ARM, the architect. Their plans get turned into blueprints by the software from Synopsys and Cadence. Then you have the nanosurgeon, Lam Research, and the precision filler, Applied Materials, who actually build the physical chip. And finally, KLA provides the X-ray vision to make sure it all works. Each one plays a unique and, more importantly, an absolutely essential role. And this quote right here, this is the thesis of this entire explainer. No single company can implement BSPDN alone. Let that sink in. If the software from Synopsys can't model the new design, ARM can't even create the architecture. If Lam Research can't edge the perfect hole, Applied Materials has nothing to fill. If KLA can't inspect the final product, then a manufacturer like TSMC can't guarantee it works, and they sure can't sell it. If any single link in this chain breaks, the entire multi-billion-dollar effort just fails.
So the crucial takeaway is this interdependence isn't just for one project. No, it fundamentally changes how the entire industry operates. It locks all of these fiercely competitive companies into a shared roadmap. They have no choice but to sync up their research and development years, sometimes even a decade, in advance just to make sure all the pieces will fit together when the time finally comes. And a huge piece of that story, you guessed it, starts with money. Just a staggering amount of it. It creates what's called the R&D money moat, the absolutely astronomical cost you have to pay just to stay in the game. You see, the glue holding this entire hidden world together is research and development. And the spending is so high, it creates what investors call an economic moat, a barrier so wide and so deep that new competitors, well, they just can't get across. Okay, let's just talk numbers for a second. In 2024 alone, Applied Materials poured $3.2 billion into R&D, just to push the known limits of what's possible with materials. How about ARM Holdings? $2 billion. And get this, that's a 75% increase from the year before as they pivot to the data center. That is a massive, massive bet on the future. Lam Research, they're in for about $1.9 billion. And almost all of that is going into perfecting these mind-bendingly precise technologies for etching and depositing materials onto silicon. And it doesn't stop. KLA Corporation spent $1.4 billion pretty much just to make sure its inspection tools are sharp enough to spot defects at the atomic scale. The scale here it's breathtaking. Now, to really put that in perspective, check this out. Companies like Synopsys and Cadence, they consistently reinvest about 35% of their total revenue right back into R&D. 35%. Most other industries, they average less than 10. It's just a completely different universe of investment. But, this moat, it's not just made of cash. It's also built out of time and knowledge. The source material makes a great point here. For a startup to even try to compete, they wouldn't just need billions of dollars. They'd need like 30 years of accumulated data on plasma physics. They'd need the trust of customers who are betting their own $20 billion factories on your gear. You can't just go out and buy that. So this brings us to our first group of hidden giants. These are the ones who manipulate the physical world on a scale that is almost impossible to imagine. Let's talk about the Iron Triangle, the true masters of physics. So here they are. These are the three pillars of modern manufacturing: Applied Materials, Lam Research, and KLA Corporation. Together, these three form a kind of triad that literally builds the foundation of our entire digital age. And that's why we call them the Iron Triangle. I mean, they don't just sell equipment. Their complete and total mastery of physics is what allows Moore's Law to keep going. They're the reason our phones and computers get smaller, faster, and more powerful year after year after year. Okay, so if the Iron Triangle builds the physical hardware, who designs the intelligence that goes inside it? Well, that brings us to our next group, the digital architects. And here, we've got another set of absolutely crucial players: ARM Holdings, Synopsys, and Cadence. These companies, they operate in the world of pure logic and software, creating the blueprints for basically every advanced chip on the planet. I really love the analogies the source material uses for these guys. Think of it like this. ARM provides the genetic code, the fundamental instruction set that says, this is how a chip works. Then you've got Synopsys and Cadence, and they act as the navigators. They provide the incredibly complex software, the maps really, that engineers use to design these chips without, crashing into the hard rocks of physical reality. Okay, so we've met the manufacturers and we've met the architects. Now for our final section, we're going to put it all together and show you how this isn't just a collection of different companies. No, it's a single, interconnected, planet-sized machine. Let's just walk through how a chip gets made. It's this beautiful chain of creation. It starts with ARM designing a new, super energy-efficient architecture. Then, engineers at a place like NVIDIA or Apple use Synopsys' AI tools to design a chip based on that architecture. Then that design gets sent to a factory, where Lam Research's cryogenic etching tools physically build the chip, layer by atomic layer. And finally, KLA's inspection machines come in and verify that every single one of the billions of transistors is absolutely perfect. You see, every step is totally impossible without all the others. So here's the key takeaway, right? These companies, they aren't really competing with each other. It's a deep, deep symbiosis. An advance at Lam Research requires a new inspection tool from KLA, which in turn enables a more complex chip design from Synopsys, which is probably based on a new architecture from ARM. They all have to rise together. And I think this quote from our source just says it all perfectly. They are integrated components of a singular planetary scale machine that is building the future one atom at a time. It's not just that they depend on each other, they're literally parts of the same machine, a machine that spans the entire globe, building our future. It's just an incredible thought. So I'll leave you with this. The next time you pick up your phone, or watch a movie, or do anything in this digital world of ours, maybe just take a second and think about that invisible machine, this silent, symbiotic, planet-sized collaboration of hidden giants that worked for decades just to make that one single moment possible for you.